From our previous lesson, you should now be able to derive and write the Kc expression for any chemical equation. It is correct to say that equilibrium constant is the ratio of the product of concentrations of products raised to the power of their coefficients to the product of concentrations of reactants raised to the power of coefficients as expressed in the balanced chemical equation. It is conventional to write the concentration of product as the numerator and the concentration of reactant as the denominator. We learned to write the Kc expression for different reactions in our previous video. Do you remember? In this video, we'll discuss the units of the equilibrium constant. The first thing you need to know is that Kc does not have a fixed unit. In some cases, it may not have a unit. It is entirely dependent on the number of moles of reactants and products. As we now know, different reactions have different number of reactants and products. Since this is the case, how do we determine the unit of Kc? Let's see. Let's first observe a case for the reactions with an equal number of moles on the reactant side and the product side. Kc has no units in the reaction with an equal number of moles on both sides of the equation. This is because the concentration units cancel out when we try to express Kc. Here's an example on the screen, where 1 mole of hydrogen reacts with 1 mole of iodine to give 2 moles of hydrogen iodide. On the reactant side, we have 1 mole of hydrogen and 1 mole of iodine. In total, we have 2 moles on the reactant side. Similarly, we have 2 moles of hydrogen iodide on the product side. As you can see, the product side and the reactant side have an equal number of moles. Therefore, there will be no unit of Kc. To verify, let's first write the Kc expression. As we can observe, Kc is equal to the square of the concentration of hydrogen iodide divided by the product of the concentrations of hydrogen and iodine. Give it a try. It's simple. Now, replace the concentration by mole per decimeter cube. We now get the mole per decimeter cube squared in the numerator. Additionally, the mole per decimeter cube multiplied by mole per decimeter cube in the denominator. Once you multiply both, you will get a square in the denominator as well. These cancel out, and therefore there will be no unit. Let's now move to the second case for reactions with different number of moles on reactants and product side. For reactions in which the number of moles of the reactants and products are not equal in the balanced chemical equation, Kc will have a unit. Here's an example, where nitrogen reacts with hydrogen to form ammonia. On the reactant side, we have 1 mole of nitrogen and 3 moles of hydrogen. In total, we have 4 moles on the reactant side. Similarly, we only have 2 moles of ammonia on the product side. We have a different number of moles on the reactant side and product side. We definitely should have a unit in this equation. Let's use the Kc expression to find the answer. For the Kc expression, we see that Kc is equal to the concentration of ammonia squared divided by the product of the concentrations of nitrogen and concentration of hydrogen raised to the power 3. We must now replace the concentrations by mole per decimeter cube. We should now get the mole per decimeter cube squared in the numerator and mole per decimeter cube multiplied by cube of mole per decimeter cube in the denominator. By solving, we should get 1 divided by the square of mole per decimeter cube. Once we square this, we should remember not to write the phrase in the denominator. Instead, we must remember to change the signs of the powers in the unit to make it the numerator. Our final answer should be mole inverse squared into decimeter raised to the power 6. Just a little more practice and you should be able to understand this perfectly. That is all for this lesson. Check out our next video where we'll solve problems related to Kc.